Suppose that we want to use complex analysis to evaluate this integral. Once again, we're going to graph what's going on in the complex plane. We'll view it as a limit as r tends to infinity of the integral from minus r to r of x squared dx divided by x squared plus 1 times x squared plus 4. Okay, so we chop it off symmetrically. Our problem points are at I, negative I, 2I, negative 2I. All right, and these are all simple poles. Okay? So, once again, in order for us to make this a closed loop, we're going to add a semicircle of radius r. Just like that. And so we would say for any value of capital R greater than 2, this loop integral is equal to 2 pi I times the sum of these two residues. All right, these residues are, of course, easily determined because they're both simple poles. So I'm just going to multiply by z minus I and take the limit as z approaches I. All right? If I imagine doing that using L'Hopital's rule, we'll find that I don't have to take the derivative of the z squared. Because if I don't take the derivative of the z minus I, then in the limit, as z approaches I, the z minus I will just nullify that contribution. So for that reason, we simply have the limit as z approaches I of z squared divided by 2z times z squared plus 4. Because in the denominator, I have something similar taking place. If I don't take the derivative of the z squared plus 1, then when I do the limit as z approaches I, it will nullify that contribution. So I'll have I squared divided by 2I times 3. Plus, here I'm going to have 2I squared divided by negative 4 plus 1 times 2 times 2I. All right? So let's see what this gives. I'm just going to cancel out one of the 2's so that I can leave it as a common denominator. I'll have I squared, which I'll take out. All right, and I'll divide. Well, here, let me just do this. not do too many simplifications too quickly. So it's going to be 1 over 6i, all right? And then it's going to be minus from that minus sign. I already took that minus sign out. 2 over 6i. All right? So that's going to give me positive pi over 3. All right? Now that's the loop integral. Pi over 3. How is that related to this integral? Well, the loop integral, so on the one hand, it's equal to pi over 3. On the other hand, it's equal to I of r plus the contribution from the semicircle. So that's going to be the integral from 0 to pi. Z is r e to the it. And we'll have that. All right? Now, we were interested in the limit as r tends to infinity of I of r. So we can look here and do integral bounds. If I call this capital E, the modulus of capital E is less than, I would have r cubed divided by, here, once again, I can say the minimum modulus of that is r squared minus 1, which is bigger than r squared minus r squared over 2. When r is large enough. Similarly here, the modulus of that denominator is always greater than or equal to r squared minus 4. All right? But I can make it even smaller than that if r is less than the square root of 8. All right? Just by doing that. All right, once again, it's the only reason that I'm doing that is to try to make it so that everything factors with r. All right, subtracting 1 versus subtracting r squared over 2. If r is greater than the square root of 2, then subtracting r squared over 2 is going to give me a smaller number than subtracting 1. So I'm dividing by a smaller number. That's why I get something that's bigger than e. At any rate, we multiply by the length of the path, which is pi. Notice, of course, the length of this path is pi r. That r is here from the differential. And so what is this? This is so as r tends to infinity, I can make this semicircular arc contribution less than any given epsilon greater than 0. Therefore, the limit as r tends to infinity of this integral is just equal to pi over 3. All right? Effectively, what happened here, this argument took a while because we were trying to do it fully rigorously. But if we look at this, effectively what happened was that the arc, the semicircular arc, sees an integral with modulus that scales like r to the 1, 2, 3. That third is from the length of the contour, divided by r to the 1, 2, 3, 4. R to the third divided by r to the fourth goes to 0 as r tends to infinity. So that's sort of an easy way to look at it.